As I pointed out in the introduction, finding the area under a curve is going to be the primary goal of our discussion of integration. Now, at this point, we have a definition of area based on adding up the areas of rectangles. But, like our definition of the derivative, it's not something that's easy to use. So our program here is going to be the same. Look for better ways to evaluate this limit for specific functions. So it looks like there's a lot going on here, but this is really just the definition of a new notation. So first, look at the setup. We're starting with a function that's defined on a closed interval. Now, the interval is partitioned into subintervals, each of which has a specific length. Now, the right side of this equation down here is just our limit-based definition of the area under a curve. Now, not only is this challenging to calculate, but it's also kind of clunky to write. So instead, we're going to use this notation on the left. Notice how this is very similar to the integrals we've talked about already, but what I've done is I've added an upper and a lower bound that match the interval we're looking to find the area for. Right, so this expression on the left is just a more concise way of saying the area under the curve from A to B. Okay, now there are a number of similarities here that I want you to notice between the two expressions. The delta x in the limit definition is replaced by dx in the integral. The individual function values are replaced by the function itself, and the sum is replaced by the integral symbol. Right? In fact, historically, the integral symbol, it was kind of a stretched out s, which is why it was used to represent the infinite sum, in contrast to the Greek sigma that we use for the finite sum. And then we have just a new word to describe this. If the limit exists, then the function itself, f of x, is said to be integrable. So now I'm going to connect this back to areas. Right? That limit that we had on the right-hand side was just the area under the curve. So what I'm saying is this definite integral notation, right? Definite because it's got that those upper and lower bounds, is just another way of writing the area under the curve. You notice in the setup up here, it starts out very familiar. Y equals f of x, and it's going to be integrable over a closed interval from A to B. You notice I did throw in one little extra caveat here. The function has to be non-negative. When functions become negative, weird things are going to happen, because then the function values are going to be negative, and when we multiply those function values by the delta x's, the areas of our rectangles are going to come out negative, and that's kind of weird, because usually when we talk about area, we only mean area in a positive sense. That's why that non-negative gets thrown in there. We're going to revisit this more in later lectures when we start looking at specific examples. It's going to be a little bit of a headache when we talk about functions that have a negative part and a positive part. So under these conditions, the function is non-negative, it's integrable, we're talking about a closed interval, then the area under the curve from A to B, the area is the same as the integral of f from A to B. Okay. So the next question mathematicians always ask, we've got this new definition, right? An integrable function. What functions are integrable? Under what circumstances can we expect that limit, that area, to exist? All right, well, here I've got a statement about that. You notice that we're once again going back to this idea of continuity, right? I said way back in the very first chapter, when we're talking about limits in the first place, when we first defined continuity, continuous functions in calculus are the good functions. They're the functions where we know that the things we want, things like differentiability and integrability, are going to happen. So that's what this theorem is saying. If a function is continuous on this interval, or, and I'm going to come back to that or in just a minute. So let's skip the or for a second. If a function is continuous over the interval from a to b, then the definite integral exists. So continuity is a guarantee. If our function is continuous, we know that this we know that this limit exists, and we can find the area. Now, there is this exception. If our function has at most finitely many jump discontinuities. Remember, that's like I have in the diagram here, where there's this gap, right? If it's got finitely many of those jump discontinuities, then we're actually still okay. Then the function is still going to be integrable. The limit still exists, right? And the reason is, if you think of this in terms of areas, right? If I take this area and this area, and then look at this part, and then this part, and I kind of treat each of these sections separately. If I do them one at a time, all I have to do to get the final area, the final integral, if you will, is just add up the parts. Right? This is kind of geometry 101. How did you find the shape, the area of an irregular shape in geometry? Well, you broke it up into pieces that you had formulas for. For example, if I wanted to find the area of a shape like this one, right, I would split it up. And I would find the area of this rectangular piece and the area of this semicircle, and then just add them together. That's all this is saying. Right? If I can break this up into a finite number of continuous pieces, then I can just add the pieces together, and I end up with the whole. Okay, so this was all very abstract, right? We defined a new notation. We have some idea of when we can expect these limits, when we can expect the area based on kind of our calculus definition to exist, right? In the next lecture, we're going to look at some specific examples, or we're going to look at some properties of this definite integral, and then we're going to see how we can actually use it to come up with some numbers for specific functions.